Okay, everyone, so continuing on with the notes, we're going to go through a couple different problems. The directions here say to find the vertical asymptotes of each function, then find the limit of the function as x approaches from the left and the right of each asymptote, then find the value of the limit at each asymptote. Okay, so we'll look at this first one. If we were to go ahead and factor it out first, because what we want to do is if we can cancel any factors, that's going to reduce the number of vertical asymptotes we would have. Okay, so first thing I want to do is factor this. So if I factor the top, I have x minus 1 times x plus 1. And if I factor the bottom, I have 2 times x minus 2. So there's nothing here that I can cancel, but remember, a vertical asymptote happens wherever the denominator is equal to 0. So a vertical asymptote in this case would be at x was equal to 2, right? Because that would make this factor equal to 0. Okay, so now what we're going to do, I'll do this in red so you can kind of see these notes stand out a little bit. So what we want to do is find the limit as x approaches 2 from the left. Oops. Of the function and the limit as x approaches 2 from the right of the function. Okay? So how are we going to do that? We are going to pick values that are really close to 2 on the left of 2, and then we're going to pick values that are really close to 2 on the right of 2 and plug those into the original function. Okay? So let's look at the first part here. I've got the limit as x approaches 2 from the left. So what I'm going to do is I'm going to use something really close to that. That would be something like 1.999, right? That's really close to 2 on the left of 2. Okay, so if I plug that into this original function, and I don't have to get exact values, I'm just trying to determine the sign of what's happening here. Okay, so 1.999 minus 1, that's going to be a positive number. Right, so that's going to give me a positive number. And then if I plug it in here, that's also going to give me a positive number. And if I plug it into the denominator, that's going to give me a negative number. So a positive divided by a negative would give me a negative. Okay, a positive divided by a negative would give me a negative. So I can then say then the limit, so the limit as x approaches 2 from the left of f of x, that's going to approach negative infinity. Okay, so this sign here is telling me if I'm approaching positive infinity or negative infinity. So now I'm going to do the same thing, and this time I'm going to do it from the right. So I'm going to say as x approaches 2 from the right. So I'm going to pick a number just to the right of 2. So maybe I'll use 2.001. Okay, so I'm going to find the limit there. So if I plug 2.001 here, I get a positive number, and a positive number, right? So I get a positive times a positive over a positive, which is also, that just leaves me with a positive. Well, that means that the limit as x approaches 2 from the right is going to be positive infinity. So what's actually happening here? I have some graph. I have a vertical asymptote here at 2. Right, this is at 2. And as x is approaching 2 from the left, I'll do it in a different color. As x approaches 2 from the left, I'm heading towards negative infinity. As I'm approaching 2 from the right, I'm heading towards positive infinity. Okay, so that's what this is telling me. And because the limit as I approach it from the left is different than the limit as I approach the function on the right, then the limit does not exist. So since the limit from the left does not, of f of x does not equal the limit as x approaches 2 from the right, we can say the limit as we approach 2 of f of x does not exist. And I know you don't have all this room on your paper. Hopefully you can kind of squeeze it in there, but that's the idea of what we're doing. Okay, so we have to find the left and right limits individually first to determine what the overall limit is at that asymptote. Okay, let's go on to the next example. So in the next example, I'm going to actually adjust this. 1 minus x is the same as negative x minus 1, right? I just multiply the top by negative 1, and then I change the order of the terms, right? And if I factor the bottom, I have x minus 3 times x minus 1. So what happens here is I can cancel the x minus 1's, which tells me that I have a vertical asymptote at x equals 3. And whenever you cancel factors, that leaves you with a whole. So I would have a whole at x equals 1. But I'm really just concerned about this x equals 3. So I'm going to find the limit as x approaches 3 from the left first. And I'm going to go back to that original function. So it's to the left of 3, so that would be like 2.999. Okay, so if I plug that in here, I have that negative first. And then if I plug that in here, that leaves me with a positive. This would leave me with a negative, and this, would leave me with a negative. And then here, if I plug 2.99 in for x here, minus 1, that's going to leave me with a positive. So I end up with a negative over a negative, which gives me a positive. Okay, so that means that the limit as x approaches 3 from the left of my function is going to be positive infinity. Now let's do the same thing as we approach 3 from the right. Okay, so if I do that, I have that first negative, and now let's go ahead, if I put that in here, so I'm probably going to use 3.001, right? That's really close to 3. If I put that in, that's going to give me a positive. And then if I put that in the first factor of the denominator, that's going to be a positive. And then if I put that in the second factor, that's also going to be a positive, right? So if I plug that value exactly in for x, I'm just determining what the overall sign is of everything. Okay? So I end up with a negative over a positive, which would give me a negative. So therefore, the limit as x approaches 3 from the right is going to be negative infinity. Therefore, because my limit from the left is not equal to the limit from the right, I could say the limit as x approaches 3 of f of x does not exist. Okay? Again, what I have is an asymptote at 3, and as I'm approaching 3, so here's 3, here's my asymptote. As I'm approaching 3 from the left, I'm going up to positive infinity, and as I approach 3 from the right, I'm going down to negative infinity. So the overall limit does not exist. Okay, in this last example, I don't have anything to factor or cancel, but I know that my vertical asymptote is going to be at x is equal to negative 1. So I'm going to check my limits to the left and right of negative 1. So as x approaches negative 1 from the left. So be careful. Think of your number line, right? Here's negative 1. So to the left of that would be negative 1.001, right? To the right of that would be negative 0.999. Okay, so when you're dealing with those negative numbers, be careful. Okay, so if I plug negative 1.001 in here, I end up with a negative number, but I'm squaring it. When you square a negative, you get a positive, so overall the whole thing is positive. Okay, so my limit is going to positive infinity, right? So my limit from the left is going to positive infinity. Let's do the same thing from the right. So as x approaches -1 from the right, so that would be like -0.999 is what I'm plugging in here. That's going to give me a positive number, and when I square that, I still get a positive number. So the limit as x approaches -1 from the right is also going to be positive infinity. And because of that, I can conclude that the limit as x approaches -1 is positive infinity. So in this graph, what's happening is here is my asymptote at -1, and my graph is doing something like this. So both are approaching positive infinity. So the only time we say the limit does not exist is if they are from one side it's approaching positive infinity, from the other side it's approaching negative infinity. Okay, let's go ahead and wrap up the notes, and basically that's what this whole little blurb here says. If the limit is increasing without bound, basically going to infinity from the left and the right, the limit is infinity. If it's decreasing from the left and the right, the limit's negative infinity. Okay? If they're not the same, we say the limit does not exist. Okay? Now, technically, a limit value of infinity or negative infinity means the limit does not exist, but we're getting a more specific answer because it's telling us what's actually happening, as opposed to just saying, nope, it does not exist. So we can't just say D and E anymore like we did like 3 or 4 days ago, because now we can determine whether it's going to positive infinity or negative infinity. Okay. On this last part here, I just want to do a quick look at evaluating or using a graph and having a bunch of different limits. Okay. So in this first one here, I'm not looking for a limit. I'm just looking for the function value at 0. So when x is 0, I'm down here at -1. So that's just going to be -1. Okay, my limit as x approaches negative infinity, so I'm going this way towards negative infinity, my graph is approaching -2. If I'm looking at x going to positive infinity, that means I'm going this way. And so there, my limit is 0. Okay, my limit is 0. Now, I have a vertical asymptote at 2. And as I'm approaching 2 from the right, my graph is tending towards positive infinity. However, as I'm approaching it from the left, I'm heading towards negative infinity. So we would say that the limit as x approaches 2 does not exist, but that's not what this last part is asking. This last part is asking for the function value at 2. And because I have a vertical asymptote at 2, there is no function value. So here we would say undefined. Okay, so there's a difference between D and E that only applies when you're talking about limits. But if I'm asking for the function value where there's a vertical asymptote, that value is undefined. All right, so that wraps up the notes for today. Make sure you complete the assignment, and I'll see you next time. Thanks, everyone.